stick snapper to snap a stick if it's not actually a stick. Similarly, it's hard for enzymes to actually work on what they're supposed to work on if there is an inhibitor there. So there are different types of enzyme inhibitors, and sometimes these enzyme inhibitors act like the substrate, act like the thing that the enzyme normally works on, but they can't be broken like a stick, and so they're kind of hogging the active site. This is an example of a competitive inhibitor, something that binds, typically these bind in the active site, so we call these like orthosteric inhibitors. They can also bind somewhere else, which we call allosteric inhibitors. But competitive inhibitors mean that they're competing for the substrate and they're preventing the substrate from binding. And with a competitive inhibitor, the thing about them is that you can overcome them as long as they're a reversible inhibitor. So there are some types of inhibitors that are like irreversible inhibitors, so they bind and they don't unbind, and so they like permanently like incapacitate this enzyme so that no matter how many sticks you give it, it's not going to be able to function. But if we have a reversible competitive inhibitor, now if we add a bunch of sticks, we can outcompete for our fake sticks, and therefore our enzyme can start acting normally. So that would be an example of a competitive inhibitor. There are also different types of reversible inhibitors. So remember, irreversible inhibitors, you get permanently stuck to the enzyme. You could be permanently stuck to the enzyme in the active site. Sometimes we see this with drugs like penicillin, where we have this sort of mechanism base, sometimes called like suicide inhibitors, where they bind and then the enzyme tries to work on it, but when they try to work on it, then they somehow change it and get like permanently stuck to it. And so penicillin does this. It takes advantage of this, it inhibits this enzyme the bacteria normally use to build their cell walls, but it gets permanently stuck on there because it kind of attacks the fake substrate, and then like the fake substrate changes in a way that's going to make it permanently stuck. There are also irreversible covalent inhibitors. So that's a covalent inhibitor. It's making one of these like strong bonds as opposed to the weaker bonds that are allowing things to come on and off and on and off and on and off. These like non-covalent bonds. So there are examples of irreversible covalent inhibitors, which I'm thinking about doing a further post on because I think they're really cool. Some examples of this in the media lately, like Paxlovid and stuff, basically these have this sort of like chemical warhead. So they bind non-covalently, so through those, like, you can let go and grab and let go and grab and let go and grab and let go and grab. But then once they've like more weakly bound, then they have a covalent bond formed, but typically from like a lysine or a cysteine or something. But these bonds are covalent, so they're stronger than these other bonds, but they're not as strong as the bonds like holding together the various protein letters and that sort of thing. And so they can be reversed, and this can help reduce sort of like off-target effects as well, but like lead to a prolonged inhibition without like messing up things permanently. And so yeah, that's a reversible covalent inhibitor, but that's a more like advanced topic, I guess. You typically, I mean, like I at least didn't really learn about those much in undergrad biochem or that sort of thing. What I did learn about in undergrad biochem were these other types of inhibitors. So basically there are several main types of reversible inhibitors. And so we can talk about competitive inhibitors, which is what we talked about before. These are typically but not always mimicking the structure of the actual substrate and kind of like competing for that active site. There are also uncompetitive inhibitors. What these are going to do is they're actually going to bind to the enzyme substrate complex. So they're going to bind to like the stick snapper once it's holding onto its stick, but they're going to prevent the stick snapping. So typically what they're doing is they're binding at some site outside of the active site. So they're binding at like an allosteric site, or they're binding at a site that is kind of created by the binding of the substrate. So I'll show you some really cool examples of this later. For like some antibiotics, they inhibit specific sequences because when that sequence is in like coming out of the ribosome, then it creates this pocket. Certain amino acids create in the pipeline create this binding pocket for the inhibitor, but other ones don't. So you're creating the substrate binding pocket when you have the enzyme substrate bound, and so your uncompetitive inhibitor is actually binding to this enzyme substrate complex. Then you have non-competitive inhibitors. The non-competitive inhibitors, they're binding somewhere else too, but they're binding So they're not inhibiting they don't inhibit the substrate from binding, so they're not like a competitive inhibitor in that way. But what they do is that they can bind to the enzyme when it's free, or when it's bound to the substrate. With this non-competitive inhibitor, so they can bind either way, and they bind like equally well in either way, so they're not really influenced by the presence or absence of the substrate in the active site, but they prevent that substrate from being turned into product. There's also a case of mixed inhibition. In this case, they can bind the enzyme when it is free, so in the non-bound state and in the substrate bound state, but they have different affinities for these two, so they prefer it in one of these two ways, and again, then they don't allow it to form a product. The different types of inhibitors, so if you have a reversible inhibitor, you should be able to like dilute it out, so it's not like permanent. But if you have a competitive inhibitor, then you can overcome it by adding more substrate. If you have a non-competitive or an uncompetitive inhibitor, then it doesn't matter if you are adding more substrate, because your inhibitor is actually preventing the actual action of the enzyme. In some way, it's actually prohibiting the conversion of this enzyme substrate into product, rather than preventing the substrate from binding. So with the competitive inhibitor, you're directly like competing with the substrate for the binding, and therefore if you add a bunch more of the substrate, then you can outcompete the competitor. You can also dilute out the competitor if these reactions are reversible. And so these are some of the distinctions between them, but how do we actually know, like, if we can't get an eye and if we don't know the actual reaction mechanisms that are going on? If we do, that's super duper awesome. But if we were to say measure the enzyme's activity with an inhibitor, we would see different types of evidence depending on what type of inhibitor it is. So yesterday we talked about Michaelis-Menten kinetics and how we could basically give enzymes like a performance review, measuring things like the Km, which is a measure of the affinity. It's a little more complicated than this, just this, but basically how good is the stick snapper at binding to the substrate, as well as the maximum velocity, this vmax. If you have a bunch of enzymes and they're working really fast, they're working as fast as they can, and they don't have to worry about running out of substrate, how fast are they working? And so the Vmax is if you have like a whole group of enzymes, and then you can divide that by the concentration of your enzymes to get this kcat, this catalytic turnover, or this catalytic rate constant, or this turnover number, which is telling you about like how good is a single enzyme. And we can imagine that at like turning things over. And so if we have an inhibitor, it's going to influence the apparent Km, so like the apparent affinity, and also like the apparent catalytic activity, and the maximum velocity and this sort of thing in some cases, but not others. Because these enzymes are acting in different ways, they have different influences on these Km or apparent Km, and these kcat and Vmax values that you're going to see. And then you can kind of like work backwards and say, okay, well, how is this enzyme working given that I have this information? And so today I want to tell you more about these various types of inhibitors and the evidence that we see for them, as well as some examples, and some kind of like future directions. I'm probably gonna do a post on the reversible covalent inhibitors because I think they're really cool, and I like came across this cool article on them yesterday, which kind of helped trigger this post, although I also did that post on Kinetics yesterday, so that helped trigger this post, and I had a bunch of graphics and stuff I'd made a really long time ago, so that helped trigger this post. All of that is to say that I've just been rambling for close to 10 minutes, and now I'm going to start actually talking with some graphics and stuff in more detail, more serious. As you probably noticed, I've gotten really technical in this post, but if you're still here and you're confused, go back and watch yesterday's, or look at yesterday's post, look at some past stuff. I'll put some links. But today I really just want to dive in and not keep you waiting too long to get to this information. Okay, so let's dive in. Another thing that can get complicated, and I don't want you to get confused, so I'm going to be talking in terms of Vmax rather than kcat. So kcat is basically the turnover number, so like a single enzyme working. And so then the vmax is like if you have a bunch of copies of the enzyme working. What gets complicated is that people kind of consider things in different ways when determining kcat in the presence of inhibitors. Do you consider only the enzyme concentration that's actually able to do work? In that case, the enzyme that's not bound to the inhibitor, it doesn't have its kcat, like its intrinsic value, it doesn't have that changed. But the Vmax is going to change. And because the Vmax is taking into account all of the enzyme concentration, like what you put in, including the stuff that's bound to the inhibitor and thus like not able to work. And so if depending on whether you consider for the enzyme concentration you're using with your kcat, do you consider like the entire enzyme concentration, or do you consider only like the enzyme concentration that's actually available, like the effective enzyme concentration? So then things can get confusing, and so I'm just going to stick to Vmax.
So let's just start by getting on the same page with some of the terminology and how I'm going to be displaying things. So enzymes can get really complicated. There could be multiple substrates. You could have multiple products. Things can be more easily or less easily reversible. So I'm not going to go into the complications. Instead, let's consider this simple case where we have a stick snapper. So in our stick snapper analogy, we have our enzyme and it's going to bind to our substrate, so our stick. And then this enzyme is then going to help stabilize like this transition state. So it's really awkward state in which the stick is snapping, so that ultimately it snaps. And so the enzyme is converting the substrate into products. And now the enzyme releases the products and it can do this again and again and again. So we're going to be considering this enzyme and the substrate free, this enzyme substrate complex, and the enzyme with the plus the product. And as we talked about in yesterday's post on Michaela's mentioned Kinetics, we can use these various values in order to kind of rate enzymes on how good they are towards like specific substrates and that sort of thing. So it's not completely this simple, but the km is basically going to be a measure of binding affinity. So it's the concentration of the substrate that gets you to half of the maximum velocity. So if you were to take an enzyme and measure its initial velocity at a range of substrate concentrations and then plot those initial velocities, you would reach a plateau at some point where your enzyme is totally saturated with substrate. So no matter how much more you add, you can't, the enzyme can't go any faster. And so basically this is the maximum rate at which this enzyme is working. Like as soon as it drops, as soon as it works, then it picks up another one and another one. It does this over and over. And so you get this maximum velocity. The maximum velocity that you measure is also going to depend on how many enzyme concentration, because the more snappers there are, the more you can snap. The fewer there are, the fewer you can snap. And so the Vmax, if you divide the Vmax by the concentration of the enzyme, you get this kcat, or this turnover number. So this turnover number is telling you kind of like the speed at which like a single copy of the enzyme is able to convert into product. So this is kind of, these are telling you about the enzyme. These are properties of the enzyme and the conditions. And so if we can, these are like constants for the conditions, but if we add an inhibitor, we can actually change how these appear when we measure them. And so if we do something that is going to change the affinity for the substrate, then we're going to affect the Km. And if we do something that's going to change how fast it can actually work, then we're going to see differences in the kcat and the Vmax. And so the Vmax is going to be directly related to this kcat. And much more on all of that in the other posts. But these are going to be the things that we typically measure, and the things that we can then see differences in the presence or absence of an inhibitor. And so let's talk about these different types of inhibitors and the different types of evidence that they lead. So once again, we have this situation, we have enzyme plus substrate. It's changed into enzyme plus product, and then this is released. And so this is how it's supposed to go, but what's going to happen when you have an inhibitor? And so as I mentioned, there are two main classes of inhibitors. We can talk about reversible and irreversible inhibitors. And so an irreversible inhibitor is going to get permanently stuck on something. So it's going to basically, there's only a one-way arrow here. Most of our arrows are two-way. For simplicity's sake, I'm drawing the kcat, so the conversion of the enzyme subs, the rate constant for the conversion of this enzyme substrate complex into E plus P, because we're going to assume that basically this product is going to be a lot more thermodynamically happy, or in our bodies, it's going to be funneled into some other pathway. And so this is going to be kept in this state where we're going to be driving the reaction forward. Also, especially if we're doing this measuring, we're measuring these initial rates, then we're not going to have product that can go backwards. And so in the simplified version, we're not considering that this is actually reversible. The key point though here is we're looking at this interaction between the enzyme and the enzyme inhibitor. And so with an irreversible inhibitor, this is a one-way arrow. So if you bind the inhibitor, now you're poisoned and you can't work. There are some different types of irreversible inhibitors, often but not always. These are involving covalent bonds. So these are involving actual sharing of electron pairs rather than the more just partial charge-based attractions and various things like that. A lot of ways that enzymes that inhibitors bind, they're often, one of the problems with drug discovery is that these inhibitors are often not very soluble. So typically, often a lot of times we focus on these charged residues and charged things like that, but it's actually hydrophobic interactions that are driving a lot of things. And so these compounds tend to be often have solubility problems, and that's a big part of drug discovery, is being able to deliver them into the body and that sort of thing. And more on that in other posts on the different types of interactions. But right now, let's just get back. And so we're just thinking about covalent versus non-covalent. You can have non-covalent inhibitors, non-covalent irreversible inhibitors, but typically they're covalent. And they often bind in a mechanistic way, or sometimes these are called suicide inhibitors, where basically what happens is the enzyme tries to use them and then it gets stuck. So bacteria build their cell walls using this transpeptidase enzyme. And normally what this does is going to attack, normally what it's going to do is it's going to attack this peptide that's part of this peptidoglycan chain in these cell walls. And this is going to help form these cross links that are helping strengthen this bacterial cell wall, these things. So these sugar peptide wall things. But what happens with ampicillin is or penicillin, various beta-lactam antibiotics, is that they kind of mimic the structure of the part that this transpeptidase normally attacks. But what happens is this beta-lactam ring is actually then going to break open. When it attacks, then this breaks open, and this is going to get permanently stuck. It can't go backwards, and therefore you have this irreversible inhibition. But now let's get back and talk about these reversible types of inhibitors, which are the ones that we're typically talking about when we're dealing with drugs and that sort of thing. Okay, so competitive inhibitors. These are the easiest to explain. Typically, competitive inhibitors are going to bind, they're going to compete for substrate binding. So often what they're doing is they're binding actually in the active site. When something is binding in the active site, we can refer to it as orthosteric. We can also we can just say an active site inhibitor. And so often these inhibitors are binding to the active site and directly preventing binding. Other times you can have allosteric inhibitors that, so we'll see a bunch of different things about allosteric inhibitors, because the other classes are also going to typically be allosteric inhibitor. We'll see allosteric inhibition, but you can also see them with competitive inhibitors. And so allosteric means it's binding someplace other than the active site, or sometimes place other than the place where the substrate normally binds. And so we have this allo, this other site. And so you can have a competitive inhibitor that basically binds somewhere else, and it's going to lower the affinity of the site for the substrate. But in either of these cases, we're basically competing for the substrate binding, we're preventing the substrate binding, and so we call this a competitive inhibitor. And if we add a bunch more substrate, even if we lowered the affinity for for this substrate binding, if we can outcompete it by adding a lot of substrate. Okay, so these two aren't competing for substrate binding, but they keep the enzyme from turning it into product. So we have in this categories, we have non-competitive inhibitors and uncompetitive inhibitors. Once again, these are reversible, so we can delete them out, unlike an irreversible inhibitor, but we can't compete it out. So we can dilute it out, but we can't compete it out. And so by diluting it out, it's just like washing it off type of thing, rather than adding substrate and being able to directly compete it. Because this is a reversible binding, if you dilute out how much there is, then there's not enough to actually like bind to a significant portion. And so you can restore the activity of the enzyme. The difference between non-competitive and uncompetitive: a non-competitive inhibitor can bind to it binds like, just doesn't care if if the enzyme is bound to substrate or not. And it's going to bind to either one of these. With a purely non-competitive, it'll bind these with equal affinity. We can also have mixed inhibition where it's going to be binding one of these preferably over the other. But in either case, these non-competitive inhibitors are binding to either of these states, but they're somehow preventing it from being turned into product. An uncompetitive inhibitor, this is going to bind only to the enzyme once it's bound to the substrate. So sometimes what can happen is that this binding can actually create a new binding site, where this is going to bind. It's like a combination of, it actually binds like part of the substrate and part of the enzyme. Other times, maybe it just makes the enzyme when it changes shape, kind of, when it binds the substrate, now it kind of opens up a binding site somewhere else on the enzyme, but not actually binding with the substrate directly. And so we'll look at some examples later. Okay, so let's look into more detail about these different types and the type of evidence that we're going to see. So remember that we're going to be talking about the Km and the kcat. So Km is going to tell us about the affinity, and kcat is going to tell us about the like turnover. So, but Km isn't quite as simple as just affinity. So you might remember like Kd, so the dissociation constant that we talk about when we're talking about binding. And so if we have two things, they can bind and they can unbind. And then at equilibrium, we have some concentrations where they're bound, some are bound and some are unbound. And this Kd is going to correspond to the concentration of one of the binding partners required for half of the other to be bound. And much more in other posts, so I'm not going to get too deep into it here. The key thing is just that, like, the lower the Kd, the higher the affinity, because it means it takes a lower concentration of one of the partners for half of the other to be bound. So either it is like every time it finds one, it's able to kind of hold on better when it picks one up. Either it has a higher like on rate, so it like grabs it faster, or it has a slower off rate, so it stays on there longer. Either way, you need less of it if you were to go and look once you're at equilibrium and look and see what proportions are bound and unbound. So lower Kd, better affinity. So with Km, here the situation is a little more complicated, because once again, we're looking at like a dissociation constant for this complex, but here we have this enzyme substrate complex. In the case of our Kd, we are only basically looking at this. But with the Km, now we have to consider the kcat, so we have to consider that the substrate can actually be turned into product. So there are two ways out of here. So the Km is also going to take into account this way out. And so the Km is going to be not just purely influenced by the affinity of the substrate, and it's also going to depend on like concentrations, like if you're at a lower concentration of your substrate, then the Km is going, like the binding affinity is going to matter more. This would matter more if you had a high concentration of your substrate, so it doesn't really matter if you're not binding it that well, as long as you can turn it over quickly. And so these are just different things to keep in mind, but we can kind of simplistically think of Km as being a measure of the affinity for the substrate. And this can be changed in the case of your having an inhibitor. And this is what we see when we have a competitive inhibitor, is we're going to see an increase in the apparent Km. And so note that this is the apparent Km, because the actual Km, the actual like affinity and stuff for the substrate doesn't change if you have a competitor there, but it's going to look like it does. So it's going to be an apparent increase. And remember, increase means lower affinity. So it's looking like it has a lower affinity. And this is because we're measuring the substrate concentration that is required to get to half of your maximum velocity. And remember that with the competitive inhibitor, we can compete it out. So when we're changing the substrate concentration, if we had a ton of substrate and compared to the competitor, then basically all of our enzyme is going to be able to bind to the substrate. And so we're going to reach the same maximum velocity as we had before. But it's going to take us a higher substrate concentration in order to get to the maximum and to the half maximum, which is what we look at for the Km. So because it takes us more, because we're competing for this. So basically it's like there's less of the substrate there that the enzymes is able to access. And so if it were to basically go and try to pick something up, it would have it's like there's less of the substrate there when there's the competitor there, because now they're going to like pick up a competitor instead of the actual substrate. So this is going to increase our apparent Km, but we're going to get the same vmax. Okay, so non-competitive inhibitors. The terms can get kind of confusing, but a non-competitive inhibitor, it's going to be able to bind to your enzyme or the enzyme substrate complex, and it prevents product formation. So you can imagine if you have some allosteric site on your enzyme system placed outside of the active site, and it doesn't get influenced, and this site isn't getting influenced by the presence or absence of the substrate, it's not going to care if the substrate's there or not. And so then but it's still going to prevent the formation into this product. And so what are you going to see on a graph is it's going to be like you have less of the enzyme, because you're kind of taking away the usable enzyme. But so what you're going to see is you're going to get a decrease in the Vmax, because not all the substrate bound enzyme is actually able to do its job. So it's like you have less of the actual enzyme than you actually have in there. And remember, the Vmax is going to depend on like your rate at which you're like actually being able to turn things over. And if you're not being able to turn things over, then you're not going to be able to reach your full capacity. And so you're going to see a decrease in your maximum velocity, or decrease in your Vmax. But you're not going to see a change in the apparent Km. So basically, because the competitor is not competing for the substrate and the competitor can bind in either of these, it's not going to influence whether the substrate binds. It's not going to affect you're not going to see a change in your apparent Km. The Vmax is lower, but you are also it's like your Km, the concentration it took you to get to half of there is not going to change, because your substrate, it's not like affecting the affinity of your enzyme for the substrate, so you don't see an apparent change in your Km. So, and Km, remember, isn't going to be affected by your enzyme concentration, whereas the Vmax will. But because what we're doing is we're effectively changing the enzyme concentration, then what we're changing is Vmax, and we're not changing Km. Okay, and also just a note that there's something called mixed inhibition, where the inhibitor has different affinities for E and ES, and then this will complicate matters. Speaking of different affinities for E and ES, when you have an uncompetitive inhibitor, now it's only going to bind to ES. So, and it's going to prevent this from being converted into product. So once again, it's like we have less enzyme, but the enzyme also has less competition for the substrate, so it appears to bind better. And so you get this decrease in vmax once again, because not all the substrate bound enzyme is actually able to do its job. However, in this case, because the enzyme substrate complexes become like stabilized once you have the inhibitor bound, even though they're useless, they're going to increase the apparent Km. They're making it like kind of, you get this increase of apparent affinity because now you're holding on tighter. And it's also going to act as sort of a sink, drawing the enzyme into binding more substrate because you're pulling away from this enzyme substrate complex. So you're using up this free substrate, and so you're going to keep, so you're basically using up this, and so you're going to keep funneling into it, and you're funneling into this, making into this useless product. So it's going to be kind of like pulling this to the right without making product. So it's like there's less of the enzyme that's available, but it's going to bind better, but it's all an illusion. This is all just an apparent change because the actual Km isn't going to change, but the apparent Km is going to change. So the intrinsic affinity for this substrate, like the intrinsic affinity of this enzyme for the substrate isn't changing, but what you measure is changing because you're getting this effect where you're taking this away. So it's tricking you. As to how this works, so sometimes you can have binding somewhere, like when you have this binding, it's going to create like a binding site somewhere on the enzyme, or sometimes it could actually be in the active site. And so this is an example of some really cool work that came out in Nature Structural and Molecular Biology. This is looking at the structural basis for like context-specific action of antibiotics. And so antibiotics, they often bind to the active site of ribosomes, so the protein-making complexes. And there are some that actually it's been known that some of these have this weird function where they're actually stall the ribosome at specific sequences. And so as the growing peptide chain is actually coming out of the ribosome, there is this the sequence that it's making is going to be like in the kind of like chimney of the ribosome. And it turns out that some antibiotics, they bind preferentially when there's certain things coming out of the chimney. So certain sequences get translated, and as they're getting translated, they're actually, the drug is going to bind only when they have a certain sequence in their ribosomal like tunnel. And what's really cool is that, so in these structures, they're showing this structural basis. And so if you have like this alanine here in this -1 position, it's actually making these interactions with chloramphenicol or with linezolid. So you can see that having a certain amino acid, so having this alanine here is actually creating a site that is for the drug, and so the drug only binds there. And so as this one group puts it, these drugs should no longer be considered as competitive ribosome inhibitors, but rather classified as uncompetitive inhibitors. And so this is an example of an uncompetitive inhibitor, and as I say, they're like a rare class of enzyme inhibitors, but a really, really, really cool example. And I will say I'm a little biased because this one's coming from my future lab, but I think it's really, really cool. So let's just recap on the types of things that we're going to see. So if we have a competitive inhibitor, it's going to bind to this enzyme in its free state and keep you from getting to this enzyme substrate state. What you're going to see is you're going to see the same Vmax because it is just, you're not changing how fast the enzyme can work if it actually gets the substrate bound. You're just making it harder to actually bind to the substrate. But if you if you have enough substrate, you increase the concentration of the substrate. Now you're able to compete for the binding, and so you get the same vmax. But you're going to see an increase in the appearance km. So it's like you have a lower affinity because it's going to take you a higher substrate concentration in order to kind of compete out all of the substrate. All of the inhibitor. If you have a non-competitive inhibitor, it can bind to either the enzyme in the free state or the substrate bound state, and it's going to keep you from getting to the product state. You're going to see a decrease in the Vmax because you're actually preventing the catalysis. You're preventing this this conversion. And so it's like you're not able to do your work as well. But you're going to see the same apparent Km because you're not changing the affinity for the substrate. With an uncompetitive inhibitor, you're going to bind to this enzyme substrate complex, but prevent it from getting to this product. So once again, we have a decrease in our Vmax because we're preventing it from actually doing its thing. But this case, we have a decrease in the apparent Km. So it's like it has a higher affinity because having this inhibitor bound is kind of like stabilizing this, and it is also pulling it out, helping shift the equilibrium so you get more substrate binding. But you're not going to, so it's like you're going to take less substrate to actually get to that half maximal velocity, but that half maximal velocity is going to be lower than if you didn't have an enzyme inhibitor there. These are all examples of reversible inhibition, where we're actually able to dilute out the substrate. So in this case, dilute out the inhibitor. With the reversible competitive inhibitor, we can compete out the substrate, or we could just dilute it out. With these two, we can't compete it out, but we can dilute it out. And if we talk about an irreversible inhibitor, that we can't dilute out, that is going to get permanently stuck. And yeah.